Okay, good afternoon, everyone. So before we start the lecture, some information. As I said last time, in last lecture, the groups are assigned alphabetically based on the tutorial you are, right? So it's like you go in this job, you're assigned to some team, and you have to work on that team, okay? So switching groups voluntarily, that's not part of the rules. Once you have the team, you're going to make a lot of decisions, but the teams are assigned, okay? And you have 1 week from now to decide which institution you want to be, okay? This is a teamwork, but at the end, during tutorials, individually, you will have to present and expose your ideas and your analysis. So if you're worried about that you're not going to be fairly evaluated based compared to somebody else in the group, then don't worry about that, because in that presentation, for sure, we're going to take into account who work harder than other students, basically. Okay. Any questions, any concerns before we start? Okay, let's get started then. Today we're going to cover the basic Solow model. Probably some of you already covered the Solow model in previous lectures or in previous classes. But today we're going to cover it from a different perspective. It's a little bit more mathematical oriented, but don't get so scared, because it's something we're going to work a lot during tutorials, in mock exams. It's about some few tricks. It's not super, super hard. Okay, so this is just an introductory slide. And the main reference is Chapter 2 of Garin et al. Garin, Lesser and Sims, the online resource that I gave you during the first lecture, and is on ECP as well. So we know that models are a simplification of reality that allows us to understand how things work. For example, in physics, Newton's laws are useful to understand some facts about the world, but not to understand other facts of the world. For example, you can simply use Newton's equation to understand an aircraft's movement. But you cannot do it for more complicated setups, or when you zoom into the world in particles. Okay, so this also applies for economic models, of course, although I need to acknowledge, and everyone knows, that economics is a social science, so it's not so exact and precise as hard sciences, right? So, and we're going to understand that throughout the course, why macro, especially macro, is super complex, because there are so many things is interacting, and there are many potential equilibriums. So it's really hard, okay? So, as I said last time, if you really want to understand something, you don't need a very, very detailed representation of that something you want to understand. For example, if you want to go to South Bank, you just need the things that you need on the way to South Bank, what bus you need to take, what are the main streets where you need to walk, and that's it, right? You don't need to know everything else. So throughout the course, we will develop these very simple models that will allow us to understand things. And those simple models, we'll call those models as elegant models. So an elegant model is a model that is simple enough, but it's rich enough that it's able to explain some facts that we wouldn't understand otherwise. Okay? So it's a model that is simple enough, that has the elements that are useful to understand the world. Okay? And now, today's lecture, in terms of these elegant theories or models, we will study the fundamental equations that drive economic growth in a very simple setup. As I said, this is the Solow growth model that you probably saw before, but from a different perspective. There will be a little bit more of math. We will study how different economies evolve from one equilibrium in terms of GDP per capita to another, how these countries transit from one equilibrium to the other, potentially. And this is something I really want to emphasize today, is that we need to learn is conditional convergence. So the the process of economies evolving from some level of low GDP to higher GDP per capita, we will understand that process through the lens of our model as conditional convergence. Who has heard that term before? Conditional convergence. Who knows what that means? Or who knows about absolute convergence? You know about absolute convergence. What does that mean? That's the mathematical definition, is it? But in terms of economic growth, which it means that a country at a low level of income will converge to a higher level of income eventually, right? So that poor countries would catch up rich countries. Okay? However, we will understand today that this solo growth model doesn't predict absolute convergence. It predicts conditional convergence. And why I want to emphasize this, because many people out there, even PhD or even economists, judge the solo growth model on the basis of absolute convergence. Say, we don't see poor countries catching up rich countries, therefore these theories are completely wrong, right? However, not even the basic solo model predicts that. It predicts conditional convergence. It doesn't predict that Uganda or South Africa will catch up the US or Australia. It predicts that countries that have similar structural characteristics, starting at different level of GDP per capita, they eventually converge at similar levels of GDP per capita. That is the prediction, okay? So that's a very important distinction that we'll learn today. And we'll also study how shocks affect the long-run equilibrium and how the transition from one equilibrium to other is determined. One difference with respect to what you probably saw before, maybe you studied steady state, how the economy goes from one steady state to the other. In the model today, we're going to have a math that is a little bit richer, that allows us to understand the dynamics, the transition path, basically. We won't just study long-run equilibrium with another one. We will also try to understand what happens in between, okay, how things move along. And that's important. So at the end, we will have a discussion about the golden rule, which is, from a normally perspective, what is the optimal equilibrium? So what is the equilibrium in the long run that we want to achieve to maximize some measure of welfare? Okay? Let me give you some historical preview, which is interesting. Solow, Robert Solow, Nobel Prize, he wrote a seminal paper in 1956. And his motivation was that two other economists, in particular Harrod and Domar, they studied this process of economic growth. They were wondering why these countries differ so much in terms of GDP per capita and in terms of how they evolve over time to get there. And these models by these two economists were inherently unstable. They had different equilibrium. The economy could go from one equilibrium to the other, which was actually really hard to rationalize with the real world, because in the data, even at that point, except for these big recessions, on average, we observe some kind of long-run trend and some kind of stability in the evolution of the economies in the medium-long run. Not in the short run, which we're going to discuss that later in the second half, but we did have this stable world. Solow tried a simple extension of the models in these two papers, and indeed, he realized the opposite, that by just making one simple change, his conclusions changed completely. So by making one simple assumption, he arrived to completely different conclusions, and he arrived basically to the fact that the economies, they can converge to a long-run equilibrium, and the way they converge to that long-run equilibrium is super smooth over time, and it looks like many economies have behaved over time. Again, except these two big recessions that we have had that will be topic of the second part of the course. And what he did, rather than assuming that inputs in production were complements, so that Leontief production technology perfect complements, rather than that, which is a micro assumption basically, he assumed that labor and capital have some non-zero substitutability. Labor and capital could be substitutes at some extent. And he assumed that that elasticity of substitution was one, which is a Cobb-Douglas production technology, essentially, right? So previous papers were assuming something like this is a production function, right? Previous papers were assuming something like this. That is the Leontief. That mathematical production function implies that you need to use capital and labor in fixed proportions. We won't go over the details, but Solow assumed something that is something like this. And that is a production function where capital and labor have some degree of complementarities, but they have some degrees of substitutability. You could use more capital or more labor to produce the same output, basically. So this is why. Okay? So just by making that change, he gained a lot of insights that we'll study today. Okay? So this partial substitutability is the Cobb-Douglas production function below here. So this is what is called Cobb-Douglas production function. Okay? Good. So we'll see that later today in the lecture. Which is an assumption that is much closer to the data. So again, this production function implies an elasticity of substitution, that epsilon is going to be elasticity of substitution. That production function implies an elasticity of substitution that is 1. So Domar and Harold were assuming that was 0. The data tells you that it's somehow close to 1, a little bit below 1. So by making an assumption that is more reasonable with the data, Solow gained a lot of insights about the world. And we're going to study that today. Okay? Good. So now we jump to chapter number 5 in the book, the online book, Garin et al. As you might anticipate, one key element of this model is the production function, right? It's not just that we have a unitary elasticities or there is this substitutability between inputs, but also we need to think about another properties of these production functions that are relevant. So the production technology, we're going to define why output. Why is output? It might be automobiles, it might be ice creams, buildings, computers, etc. That's why, right? That is our why. And then we're going to have inputs of production. So the production function essentially transforms inputs into output, right? It's just that. Inputs, we have capital and labor, right? These are our two inputs. And we have the level of technology A. And here I want to stop a little bit because I have an interesting question last time. From that production function there, up there, you got output, yt is equal to at f of k, t, and t, right? And an example of that is this, is yt, as I said before, at, kt, t is time, okay? Time t. Alpha is a fraction of capital in production. Alpha is just a parameter of that production function. It's a share, okay? And t is... So somebody asked and said, we were talking about Hall and Jones and this social infrastructure, productivity, in last class, right? Who was that? Somebody here. Who asked me about this? Well, she asked me, she said, but isn't the case that AT is technology? Like you create a computer that is more efficient, or you have a machine that is more efficient given some certain type of inputs, right? And that's a concept we typically have, like AT being this productivity or technological progress, which is one way, of course, of interpret this. However, that's an aggregate production function. Do we have an aggregate firm in the real world? No, right? So in the real world, we have so many firms in different industries producing very different things. So when we think about the economy at the aggregate level, that AT up there, what is that? It's just a residual. It's whatever is not explained by capital and labor that affects output. So AT is whatever is not capital and labor that affects output. So that can be the quality of institutions in a given country, the market, the credit conditions that allow some firms to invest and others don't, market power. It can be a bunch of different things that affect output Y that are different from K and N. So that residual that is typically known as technology or total factor productivity can be many things. And Hall and Jones, they try to proxy that with a variable that is called social infrastructure. So we'll see that in detail in lecture 5. We talked about that last week a little bit. But while AT is typically interpreted as technology, it's much wider than that. It's more general than that. Okay? Does that make sense? Okay. So let's keep going then. This model will have, of course, the production function, and on the other hand, we'll have accumulation of physical capital. Households, suppose you are households, you are going to invest and buy computers or machines, tractors, you will have those. And then you buy them, why? Because you rent them to some firms. So you buy this physical capital as an investment because you get a return, which is the rental rate of that. You rent it to the production units, the firms. As a household, you buy that to rent. So there will be this physical capital accumulation investment. There will be labor force, so workers that can grow at some rate. And there will be this technological progress, but again, this is much general than that. It's not just technological progress. This is not a fully microfounded model, and here I don't want to scare you so much about microfoundations. What I want you from this course is to be able, that you are able to understand in the first part, economic growth facts and theories from an analytical perspective. While mathematical tools are going to be needed and important at some point, I don't want to emphasize that so much. And if I really feel that I want you to solve any complicated mathematical problem, you will have a mock exam then to practice, and I will give you some guide before. But rather than that, I really, math is a tool, but at the end I really care about the economics of this, okay? So I'm going to skip those and go over the details of the model. Well, on the back of all this model, this is what's going to be happening. There will be infinitely many identical firms. The fact that there are so many implies that none of those firms has any influence in market prices. If suppose you are 1,000 firms out there, right? Whatever you do, given that you're so small and all are identical, doesn't affect equilibrium prices. So you're going to be price takers, okay? Which implies also you're going to be in competitive markets. Time is going to be discrete and will run forever. There will be, as we know, firms, in order to produce YT, they need capital and they need labor. For capital, they pay RTKT. So that RTKT out there, that is what the firms pay to the household by renting to rent a machine or to rent the computers. And then you have as well over here the wage bill. There will be workers, and the firms will pay money to these workers. Okay? The fact that I'm caring about the details of the firm problem is because firms in this, the more microfounded part of this model is firms maximizing profits, which is going to pin down prices in competitive equilibrium, and that will allow us to understand what happens to the economy and to prices, to wages, to rental rate of capital when there are some shocks to the economy. There will be this firm productivity, AT, but again, it can be wider than that. It's not just productivity. And as there are infinitely many identical firms, the same applies for households. Okay? And households are going to work at the market wage. So your households, there is a wage out there, and depending on the wage, you're going to decide how much you want to work. That's typically how it works. However, we're going to simplify this much more by assuming an elastic labor supply. You might anticipate why I talked about elegant model before. This is a super simplified model, but it's rich enough to understand things that are happening there. Okay, so households will make consumption and investment decisions. Okay, so the household will go in to the shop and buy apples to consume and other apples to invest, or think about different goods, like automobiles to consume and automobiles as an investment, that they will rent to some firms that will be taxi drivers. So then the resource constraint of the economy, there is no inventory, so all what is produced is equal to what is demanded. So YT is the supply of goods. And this over here, consumption plus investment, is the demand from the household, the demand for goods. So in equilibrium, these two things are going to be equal, like market clearing condition or resource constraint in this case. Okay? CT is consumption, IT is investment. So the cars that you buy and then you use for investment purposes. Demand for goods and supply of goods. Okay, so we are also assuming that the household will own the firms. You are the households, you will buy stocks, shares from different firms, and the firms will pay you some dividends, so you own the firms. These are strong assumptions, but don't freak out, because these are just assumptions that are useful from I won't pronounce well that word. So in order to teach you the right mechanisms, we need to make the simplifying assumptions. Then when economists go work in a central bank, or when you are consulting at some government institution about some potential problem, the models are going to be much more general, right? So, but now we're making these assumptions, although in modern macro and central bank, we relax most of these assumptions. So please don't be discouraged by this. So in macro, for example, we know the importance of firm level heterogeneity, of household level heterogeneity, and now after the financial crisis, and not just after that, but also before, there was a lot of research about that. We know about the importance of financial markets. Okay, so the thing is that even when these simple models are not realistic, all these mechanism that we find here will apply in these very big models. Qualitatively, all this mechanism will be there, but quantitatively, one might not be that important, and you can have another mechanism that might be dominant when you think about designing policies, for example. Okay? Good. So now, let's think about key elements of the production function. The production function f of Kn, where K is capital and N is hours worked or number of workers. It displays the diminishing returns, diminishing marginal products. Who has heard about this term, diminishing marginal products? Okay, so diminishing marginal products is here. Suppose you have capital, K, and here you have YT, which is production, right? When you add one machine, suppose there are 10 workers, right? There are 10 workers in this company. and you add one machine, you're going to increase production. You add another machine as well. But then, as long as you keep increasing the amount of machines that you put in the production process without changing the other input, which in this case is labor, there's going to be decrease in returns. Because at some point, there won't be anyone that can operate that machine, right? And you can even think in a case where these machines are going to create some kind of chaos and even reduce production. But we're going to think about as diminishing returns, which mathematically means that first derivative, delta F, delta K, that's how much F, how much production changes when capital changes, right? So you might think of this, and a professor I had in Virginia, he used to do this, like, this is like the change in F, Kn, when you change capital. So that partial derivative there, you could think about that as a proxy. How production changes when you change capital. We know that's positive in that graph over there, right? But we also know from that graph that is F, right? So you don't get confused. While we know that that is positive because it keeps increasing when you increase capital, we know that also it increases at decreasing rates. This is a concave curve because of diminishing marginal products, which means that we have that derivative that there. The second derivative, so the change in the slope is negative, is concave. Just think about a concave production function that intuitively in your mind has this concept of diminishing returns. Because if you keep adding machines or given the amount of workers, production won't increase all the time as much as it would increase at the beginning, right? So it's that's an important and very sensitive way to think about the world. Okay, so all else equal, the contribution of inputs to production decreases as we increase inputs. And this not only applies to capital, it also applies to labor. Okay? It also applies to labor. So the same applies for this and for this. So the same applies for labor and capital. And here, another important thing. What do you think is the sign of the cross derivative? Which is this here. That is like the marginal product of capital. Like the marginal product. Sorry, I'm old. The product of capital, right? How do you think that the marginal product of capital changes or is affected when you increase the amount of workers? And that is mathematically this. That is saying, how do you think that the marginal product of capital changes when you change labor? Is that positive or negative? We have 10 machines, 10 computers, and 10 financial analysts. We add 2 more financial analysts to the team. Do we produce more reports or less reports? More, right? So that is positive. And what is that? That is a complementarities in production. Okay, so we have this assumption that even though marginal products are decreasing, we have this concave curve. The marginal product, so the additional contribution of a given input, increases when you add the other inputs, the cross derivative. So this is complementarities. And why this is important? This will be important when we think about the evolution of wages. Because we'll see that wages, or the rental rate of capital, are functions of these marginal products. I don't know if you have heard that the wage is equal to the marginal product of labor. Have you heard that? Like the additional contribution of production, that should be equal to the wage of that worker for firms to maximize profit. We'll see that later. But, okay, so if the wage is equal to the marginal product of labor, and I have the productivity term there because that's actually the right thing when you think about output. But why we need these complementarities? Because what happens if we're in a world where a wage is determined that way, and then suddenly there is an earthquake or something that kills the machines or destroys the machines in the economy? So in that world, then what happens with the wage rate? Will the workers become more or less productive than before? So that's why, in this case, actually the wage would go up if we think about that. So the cross derivative matters because what happens with the wage when capital changes? So what happens with the marginal product when capital changes? We'll see that in the next slides, but I just wanted to introduce this concept. These concepts are important, okay? Is that clear? Anyone has questions or concerns about these concepts? Okay, so you can go. No, you want to go, right? It's Friday. Okay, so F also has constant returns to scale, which means that if you increase each of the inputs by A, where A is something larger than 1, output will increase by the same amount, okay? And this is what you did in tutorial, right? In tutorial, you look at different cases of constant return to scales, decreasing return to scale. So I will skip this. I will just mention that it's important for us, this assumption, because it implies that the derivative or the marginal product of big F will be equal to when you take derivative of marginal products with respect to little f. And what is little f? This is little f. When you divide total production by n, here, when you do this, then you can also work out the right-hand side of that equation and multiply by 1 over n each element of that production. Right, so which is this. So little y is just big Y over n. And this is equal to 1 over n A F K n. And that 1 over n there can enter that big F when we assume constant return to scales. Which means that we can do this. That 1 over n that is outside that function, given that we assume constant return to scales, can enter that function. And then it will be just A times F of K over n and n over n, which is 1. And that we can convert later to just, so basically A, F, K over n, comma n over n, right? That is equal to A, F, little k, comma 1, where little k is big K over n. Little k is just big K over n. And then we just define that as little f. It's just notation. That big F of little k, comma 1 is just our little f. And given that we assume constant return to scale, we can work all that out, and at the end, the derivative of the big F with respect to the big K, it will be equal to the derivative of the little f with respect to the little k. And that will be useful later, okay? Keep that in mind. You don't need to know all those steps, but you do need to know why we are discussing this and why it's as important.
I don't understand why over n is
So, do you understand the concept of capital per capita? What do you say? Sorry.
Capital Y over I thought
Yes, so Y over N is output per person, right?
Yeah.
Or GDP per capita, right? K over N will be, yes, so Y over N is output per person, output per capita, GDP per capita. That little y. Little y.
Stand for the labor, the hours labor provided, right?
So in this simple model, there will be actually population is N, and they are all working. So is output per person, is output per hour, is the same thing in this simplified model. Yeah, so income per capita by definition is little y, right? Or you're asking why income and not product, output? So I don't quite understand your concern, sorry. Yeah, which is income per capita, or GDP per capita, or output per capita. Yes, the number of people in the economy per capita. But income per person is income per capita, is the same. Or income per capita is referred as income per person. Yeah. The distinction is income per worker or GDP per worker. But typically per capita is divided by the number of people in a given economy. So when we do the homework, we can do GDP per capita will be total output, total GDP divided by population. N. And in this model, population, all they work. So it's the N is people and workers. Then when we go to the data, we can do GDP divided by population or GDP divided by workers. But we'll try to stick to population N, which is per capita or per person. Maybe I'm missing something in between. I'm pretty sure per capita is the same as per person. I think I'm right there. If somebody heard something else, let me know. But yeah, per capita per person, at least in this room. Okay, so capital accumulation of capital follows this law of motion. So this is an equation that describes how machines evolve over time. Okay, there will be a depreciation rate delta. Which means that a fraction delta of the computers in this room will be useful next semester. But, sorry, a fraction delta of the computers or the equipment in this room will be useful next semester. Will not be useful next semester, delta. So the 1 minus delta, right, this one here, is the undepreciated part of physical capital. Delta is the part that is not useful, and it's going to be just wasted, right? So this is a stock variable. We have an amount of seats, equipment, boards, computers, and they carry on for next period, t plus 1, the fraction that is undepreciated, the fraction 1 minus delta. But at the same time, we have investment, right? So I is investment. The new amount of computers, the new amount of seats that we put in this room. And delta is the depreciation rate of capital, right? I just said that before. And then this equation here is the key for this model. This is a dynamic equation that, given the assumptions that we have made already, will determine the long-run equilibrium of the economy and also will determine the transition path of this economy. So this is super important. This is an assumption that we make, how capital evolves over time, which is pretty much standard, not only in when we think about capital, also when we think about other stock variables like even human capital. We can think of that. We can think of this as assets as well. They have this law of motion. You carry on to the next period some assets, others you sold, others you keep, and you buy or sell some. So that's a law of motion basically for these dynamic variables. So then we also assume that this is an important assumption. We're going to assume that investment is just equal to a fraction s, little s, of total output, right? So from the total production out there, from all the chairs, all the computers produced by firms, households will use part of those, fraction s, for investment. And the other fraction will be used as consumption, right? So then we also know that yt is equal to this production function. So then we can boil down everything to the properties of that production function. Okay, so that's an assumption. It's a very simple assumption, but again, it avoids to complicate this from a mathematical perspective. We could write down a model where households maximize utility subject to some budget constraint and subject to some dynamic decision of investment. And that will imply an Euler equation, a dynamic equation that will imply a path for consumption and investment, and that will be all super complicated. But at the end, will also give us the same idea that a fraction of output is saved or invested, and another fraction is consumed. So for the ones that are interested in this more micro-founded version, that's a link for one of the chapters in lecture notes from Eric Sims, which is one of the authors of this book. Okay, so let's keep going then. And now, so what we have here, this equation, is the equation that determines the evolution of capital over time. Now we need to understand how wages and how the rental rate are determined in equilibrium. How do we think about the wage, which is potentially a measure of how workers are, the welfare of workers, how they have been paid, how much they can buy, and how happy they could be. And where are we getting these prices from, the wage and the rental rate? From a maximization program. And this is the most mathematical oriented part of this, which is basically that the representative firms in this economy will maximize profits. Okay? When you maximize those profits, it turns out that you can obtain from the first order and necessary conditions of this problem what is the wage and what is the rental rate of capital. Who knows about maximizing a function? Who knows about first order condition? Who doesn't know anything about maximizing a function? Who knows a little bit of maximizing a function? Who wants to take a break? You want to take a break? Okay. So let's take a break. 5 minutes break and then continue. Now, yes. Okay. So firms in our model are rational agents that maximize profits. What are profits? Profits are this pi t term over there, okay? What is the definition of profit is just PT, YT, where PT is the price of these apples, the price of the ice creams or the product that is produced. YT is the amount of ice creams minus what you need to pay to your inputs in order to produce, right? Minus W and T with the wage bill minus the rental rate of capital times the amount of capital you rent. Those are your profits. And these firms want to maximize profits, okay? Before we maximize and we do the math, I'm going to normalize. You don't see the price of YT. You don't see PT out there in the formula in the slides, right? Because I can just normalize that and assume that PT is equal to 1. Why can't I do that in economics? Why? Sorry, can you speak louder? Law of one price. Okay, who can rephrase this? What, do we care about absolute or relative prices? We care about relative prices. So to make marginal decisions, we care about whether the workers or the capital became more or less expensive in relative terms. So we do care about relative price, meaning that we can just normalize one of the prices here because we want to measure everything relative to whatever else is there. So we have the price of labor is the wage, we have the price of capital, the rental rate, and we have the price of the output. Given that to make our economic decisions, we just need to know relative prices. We can just normalize that. You could normalize the wage rate to be 1, or you could normalize the price of output to be 1. And that's what we're doing now. Okay, so now let's maximize. These rational firms, in order to make their decisions, they maximize their profits. And this is just from math that we're going to just borrow this for today. We know that when we want to maximize a function under no constraints, so this is an unconstrained maximization problem, we just take derivatives with respect to the control variables. What are the control variables here? What are the variables that we can manage? Labor and capital. The firms here are going to decide the optimal amount of labor and the optimal amount of capital such that they are maximizing profits. And that is mathematically just taking first-order conditions. The first-order conditions are two things in this case. With respect to capital, equal to 0. That's the first-order condition with respect to capital. When we do that, we will find either a formula for capital or a relationship that describes the optimal decision of capital and labor. Those are the mathematical conditions for firms to pick labor and capital optimally. Okay? Just take that as given from a mathematical perspective. We're going to do that. Once you do that, this is what you get. Once you maximize once you do that, when you take the partial derivative with respect to NT and equalize that to 0, you obtain that equation out there. What is that saying? That the wage equals the marginal product of labor. That the right-hand side there is the marginal product of labor. So given that we are in competitive markets, firms, suppose you're firms, you're so small that you don't have any control over wages, over rental rate. What you can do, although, is to pick labor and capital optimally. And you do that until that happens. Why? Suppose this is the case. Suppose that the wage is smaller than the marginal product of an additional worker. What do you do there? You hire one more worker. What's your name? Daniel. I want to learn 3 names today. Daniel. And what's your name?
Shihan.
Chino?
Shihan.
Shihan.
Yeah.
Shihan. And from Singapore, your name?
Navid.
Navid?
Yeah, Navid.
I forgot all your names already. Shihan and Navid.
Yeah.
And Daniel. Okay, so suppose that Daniel wants to hire Navid. I forgot your name. Navid. But this is happening, so that the wage, because you take that as given, you take that wage as given, it's there in the market. But when you hire him, it turns out that still the marginal product of labor, because you can evaluate that right-hand side thing. We know F, we know the number of N, we know the machines that we have, and we can have a measure of that right-hand side thing. What if that's the inequality there? That is telling us that still, if you hire one more person, that person will contribute to production marginally more what you have to pay to that person, basically. So you need to pay to that person wage. Say that again. Shihan. Yeah, you could still hire him, Shihan. You can still hire him and keep increasing profits. Why? Because the marginal product of him is larger than the marginal cost of hiring him. That means that you can keep increasing profits. And you keep doing that as long as, until the equality holds. And if the inequality was the other way around, you have to fire them, one of them, to be maximizing profits. Okay? So that's intuitively what's going on here. Now, when you do the same for the rental rate, it's similar. The cost of renting a machine that is given out there for you to be optimizing has to be equal to the marginal product of that additional machine. The marginal product of that additional machine equals the rental rate, and the wage equals the marginal product of labor. That is where these firms are optimizing. Okay? Good. So now we take these two equations as given. These equations are how we understand, how we back out what is the wage in the economy and what is the rental rate of the economy. Okay? So now we can know from whatever happens to K or N, we can infer what happens to W and R. That's essentially these equations are telling us. In competitive market, with firms that behave this way, these are the decision of K and N that we observe, then we can understand and know what is the wage rate, what is the rental rate. Is that clear? Okay, so I'll leave that question there for the ones that are curious. Okay, so the equations that characterize our model are the production function, how you convert inputs into outputs, the goods market clearing condition, or the resource constraint if you're thinking from a planner problem. Total output has to be consumed or invested. The evolution of capital, that is this law of motion of capital where KT plus 1 is equal to what you invest plus the part of capital from today that can still be useful for next period, so the undepreciated part of capital. The investment decision, because we assume that it's just a fixed fraction of output, although we could do it much more complex, but we don't want to make things more complex if they are not super useful to understand our mechanisms. Okay, so we want to stick to this. The equilibrium wage rate, as we just saw, is equal to the marginal product of labor. And the equilibrium rental rate is equal to the marginal product of capital. These are our key equations of the model. So this describes our economy, this describes our environment. And now we'll start to study the transition dynamics and the long-run equilibrium. Okay? Is that clear? Good. So these are a set of equations that have a lot of things going on the behind the scene. Agents maximizing, making some decisions, and making these assumptions about the model. Okay, so let's take let's find the key difference equation in the model. What is that? So remember that this is just investment, IT, which is just little s, YT, and little s, A, F, K, and T. We're just replacing what investment is. Investment IT, capital IT, is just little s times YT. That is just by definition. So we are replacing that there. So now divide everything by NT. Why we want to do this? Because we are interested in output per capita, right? We are interested in GDP per capita in the long run or along the transition. So we're going to start dividing things by N as a measure of welfare. We're going to think about output per capita. So let's divide everything by NT. And let me try to do this so you realize of some important tricks here. So we have KT plus 1 divided by NT equals to S AT F KT NT plus 1 minus delta KT. And let's divide all the right-hand side also by NT, right? So we are dividing the whole thing by NT. And you will have to do this when we think about this model extended. Sometimes we're going to add new features to this model. And then all the time when you want to think about long-run equilibrium and measures of per capita, you will have to divide by NT or potentially by something else. But this is just an important trick. On the right-hand side, things are very, very straightforward. So let's just start from this. What is KT over NT? Little KT, right? Little KT. Okay? What is now big F over NT? Little y. Yeah, that's actually right. Little yt. And here, what is that thing? That is not little kt plus 1, right? So we are mixing t plus 1 with t. So the trick is, it's a very basic trick, but students usually get confused with this, so that's why I'm going to just do it. Can I do that? Why can I do that? Just 1, right? So I'm just multiplying by 1. But the trick is that once I do that, I can essentially put these terms together, these two things together. And what is that? A little kt plus 1. And what else I got there? Nt plus 1 over nt, right? And what is that equal to? What? 1 plus the growth rate? Yeah. That is 1 plus the growth rate. Why? The definition of the growth rate of a variable, say growth rate of n, the definition is nt plus 1 minus nt over nt. That's a definition for growth rate. If you work out that, then you have that 1 plus gn is equal to nt plus 1 over nt. So nt plus 1 over nt is just the gross growth rate, 1 plus the growth rate. So here we have 1 plus the growth rate of n is equal to s times little y, and little y is also a times little f, if you remember from before. So that dynamic equation out there that we have in terms of per capita describes the evolution of our economy, the dynamics of our economy. and also will determine the long-run equilibrium. What I did here is just for you to understand that trick. Now I will show you the equations from the slides that are just working out this. I'm just doing the same thing out there, where I multiply by this guy over here, which is just 1, reorganize terms, then, and have that equation out here. That is our key equation, dynamic equation. And assuming that n is 0, what is little n? In that case, here, little n is just the growth rate of n. That is little n. If we assume, like we're going to assume today to simplify things, that n is equal to 0, however, in tutorials you won't assume that. In tutorials you will change that. That equation in blue there is what I call the TD equation. It's a TD equation because it's a transitional dynamics equation. Okay? Transitional dynamics, TD equation. Our TD equation will be fundamental to understand our mole. And what does it say? It says that tomorrow's capital per capita depends on today's capital per capita, the part that is undepreciated, plus investment per capita. It's just the same thing, but now we can actually work this out in a graphical way, and then we can then find out a long-run equilibrium. How do we do this? Just from this TD equation, right here, we can now make a graphical analysis of the mole. How do you think that equation is going to look like in terms of shape? On the right-hand side, we have KT. The last term is linear on KT. But the first term is concave on KT. That's why the properties of F are important, right? This is concave on a KT. The other term is linear on KT, little KT. But given that little f is concave, then that will determine the concave shape of that TD curve. So if we graph, if we put in a graph little kt and little kt plus 1, on the y-axis, we're going to have a concave function. And that's the next graph, basically. So I'm just... this is what we have here. So this is our TD equation, transitional dynamics equation. The x-axis is kt, little kt, capital per capita. The y-axis is capital per capita tomorrow, t plus 1. And this curve over here, that one here is just the 45-degree line. The 45-degree line is just kt plus 1 equal kt. Little kt plus 1 equal little kt. Okay. How do we know that these curves intersect? That is in the next slide, okay? Given the properties of the production function, we know that these actually intersect the 45-degree line. For the ones that are more interested in math, it's in the next slide. But I want to focus on the economics behind this. That intersection implies that there is an equilibrium at some point in time where little kt is equal to little kt is equal to little kt minus 1 is equal to little k star. Okay? That intersection implies, as you can see out there, that kt and kt plus 1 are just equal. And that is equal to little k star. That is a long-run equilibrium. Once the economy arrives there, it stays there. That's the stability I was talking about from the solo growth model. Okay? And So let's think about how the economy gets there by using the transitional dynamics equation. Okay? So say that we start little k is 0, or little k is 0. Let's not assume anything about a year, but it's just little k 0. Okay? We start at little k. This is the amount of machines, this is the amount of computers that we have in the economy today. What does the model imply for tomorrow's capital? Given that there will be some investment and there will be some undepreciated part of capital, our TD equation tells us that tomorrow's level of capital per capita will be here. Right? Why is that? Because we start at little k0, and then our transitional dynamic equation up there, that concave curve, predicts what is future capital based on this model, basically. That is little k1 tomorrow. Okay? Is that clear? So I'm just starting from any given point, little k0, and then using our transitional dynamic equation to infer what is tomorrow's capital. This one. This equation here is just little kt plus 1 as a function of today. Right? So you can think of this equation also as little k1 equals s a0 f k0 plus 1 minus delta k0. Right? And you can write down that equation for every period, like little k2, little k3, little k4, until you reach a steady state, mathematically. But graphically, we start at little k0 over here, we go up there in the graph, and we get to little k1, and then we go one period ahead then. Let's now go here, from here, to the 45-degree line, and let's go one period forward, and we are now standing at period 1. That's why we need the 45-degree line. We're standing at that period 1, at that level of capital that the TD equation told us the economy was going to be. And then what is going to be capital in period 2? How do we know that? Again, we have the formula from the TD equation. We just go up there again, and we find out what is the level of little k2. Right? 2. And we just keep doing this until we reach. We do that again. 3. And then we come here. We got little k4. Until we reach the long-run equilibrium, where, say, suppose that this is reached at period 7, say. And then we find that it's just at some point the economy reaches this long-run equilibrium. Okay? So this is what this simple model with these simple equations implies for the transition and for the long run, right? So one thing you have to notice here is that the decrease in returns, the diminishing returns of capital imply that the marginal increases in capital, these jumps from the red to the green and to the blue, the increase in capital is every time smaller and smaller, right? So that implies that the economy will go from one equilibrium, in K0, to the other equilibrium, K star, in a smooth way. So capital will increase, but then won't increase so much until it reaches that. And that can be seen in the next figures, basically. Is this clear? Is this clear to everyone? Okay, good. So now, as I said before, we can think about the existence of that equilibrium more formally, and this is what a this slide is about, but I will just skip it. You don't technically need to know all these details in the test, because we're going to know that the equilibrium exists, everything's going to be there. But it's interesting to understand why we can actually claim that that's an equilibrium. And that equilibrium is there, and we can prove it because of the properties of the production function, because of diminishing returns, and because of the fact that there are INADA conditions. The INADA conditions imply that if you put one input, you increase it so much, the additional return of that input is eventually zero because of the diminishing returns. So if you assume that extreme, or the other extreme where you don't have any input, so there are 1,000 workers, but there is no machine to operate. We put one machine, the productivity of that machine is huge because there are so many people that can help operating that. So that is essentially INADA conditions. Again, this is technical, formal. If you're interested, you can take a look. We can discuss that later. But now, and this graphical analysis is exactly the same as what I already did with the pen. And this is graphically how this looks like. So here, this is like our little k0. This is like our little k1 and our little k2, right? So in the x-axis, we have time. This is a dynamic system and a stable system. We have time here. And in the y-axis, we have the level of capital at some certain level of time that is indexed by J. So if you look at that, the evolution of the economy from time 0, little k0, to the long-run equilibrium, k star is concave, right? And that is when you went from k0 to k1, there was a big jump. Then the jump was smaller, diminishing returns, and smaller and smaller, and that is the shape of this curve, basically. That is concave until you reach that equilibrium. And the same will apply if you start from a lot of capital. If you're in an economy that is over-investing, basically, you will do the opposite. You will start decreasing capital gradually to get to that. So that will be this over here. You were over-investing, and you start reducing until you get to the steady state. Okay? Good. So now, from this evolution, we're now going to think about economic growth and the long-term equilibrium as well. So here, I'm going to skip this. I'm going to skip this today because it's pretty obvious that actually I'm going to just simplify these slides by this. I'm going to just do this manually. Suppose that we have this production function y is equal to a k n, right? And suppose that it's actually a Cobb-Douglas as we had before, right? Suppose that's a production function. Now let's have a more precise definition of little y. Little y, or GDP per capita per person, is that. And I'm just dividing this two part of this equation essentially, dividing by n, right? I'm just dividing this by n. When I do that, the big Y becomes a little y, and then when I do that on the right-hand side, what do I have? I have this. Right? So, what is that equal to? We got n in the numerator and in the denominator. What do we know about that? Exponents they add up when you're multiplying and they are subtracted when you're dividing, right? So it's just n to the 1 minus alpha divided by n is just a k alpha and n to the power of 1 minus alpha minus 1, because you got the 1 in the denominator from that n. And that is equal to a k alpha n minus alpha. This one cancels with that one over there, and you got n to the minus alpha, which is equal to a is equal to that. N to the minus alpha is just the same as bringing n to the denominators as n to the alpha. Therefore, what we have is that little y is just a little k alpha. By definition, little k is just big K over big N. So I'm just using that definition to have this. So, what do we know about the long-run growth of GDP per capita, little y, in the long run? The growth of that y. And we also learned this in tutorials, I think. Yes. That the growth rate of little y is approximately the growth rate of A plus alpha, the growth rate of K, little k. The way you obtain that is by using the tools you learn in tutorial, which is take logs, take first differences, and use the approximation that the log of 1 plus the log of 1 plus n is approximately equal to n. So this is what you should have done in tutorials, that you take logs, then take first differences, t plus 1 minus t, so basically, yeah, and then because this is t, 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 you take logs and then take the first difference to have something like take logs, the log of yt minus the log of yt minus 1, that is equal to, etc. You work that out, use the tools from tutorials, and use also the fact that the log of 1 plus g, where g is a growth rate that is small, and we saw that in the previous lecture, the log of 1 plus g is approximately g for small values of g. So once you do that, which is following what we learn in tutorials, we know that, in blue, over there, that the growth rate of GDP per capita is equal to the growth rate of technology plus alpha, the growth rate of capital, right? And what do we know about the growth rate of capital in the long run? What is that equal to? What did we learn about the economy previously? That it converged to an equilibrium where little k stays there, right? Therefore, in the long run, what is GK? Zero, right? In the long run, given that little k is just 0, because the economy stays there, then that term in the long run is 0, the right-hand side term. In the long run, which color I can use? In the long run, LR is long run, okay? GK is 0. Therefore, long run equilibrium, GY, would only be positive if there is long-term growth rate of technology, right? That GA over here. the only way that the economy can grow in the long run in this model is that if technology keep increasing over time. That is the way the economy could grow. But at this point, we're just assuming that A is a constant. There's no process behind that. So given that A is just a constant that sometimes can change, but it doesn't have a proper growth rate for now, this means that this model implies a growth rate for GDP per capita in the long run that is equal to 0. And we know in the data that's not true. We know that Australia, the US have a growth rate in the long run that is about 2%, right? We saw that in the previous lecture. Okay, so that's what I just showed you is another way of doing this. So you have varieties of way of thinking about this. What I just did, what is here as well. But the main point is that the only way the economy will grow, will grow in the long run is if there is growth in A. Okay? Only if GA is positive, then GA is positive. Otherwise, there is no long-run growth, economic growth. Investment or capital accumulation doesn't have long-term effects, basically, just short-term fluctuations. There is a lot going on from capital accumulation for investment, but only in this transition. In the long run, no, the economy attains that long-run equilibrium and stays there under these assumptions. Okay? Good. So now, we need to understand, we're going to understand the levels. Let's come back to our transitional dynamic equation, okay? And let's think about now the long run. And again, we're going to impose what we showed graphically, that this economy will converge at some point at some long-run equilibrium. So this is our equation. This is the equation that we have over here. And we know that the economy attains this longer-run equilibrium. Yes?
Can you just go to the previous slide again?
This one?
The one where you opened everything. Is it gone now?
Right here.
Oh, okay.
All good? Everyone on board? This will be on the... Also, I will post these lecture notes also after the class with all these notes, okay? I mean, it's also important you take those notes now, of course, but they will, all this is going to be in Blackboard. Okay, so here. Now let's think about long-run GDP, long-run capital per capita. That is our transitional dynamic equation. Let's find an expression for K star. So I'll give you 2 minutes to try that, and I will give you this hint, which is that we know that long-run equilibrium implies that capital per capita is just constant. So use that, replace that into the equation, and find an expression for little k star. Okay? You got 2 minutes to try that out. Don't look at the slides. Just try to do it by yourself. Find the expression for k star based on that equation. Based on those two equations, basically. The one that I gave you and the one that is out there. Without looking at the slides, huh? Zurdo.
You're putting pressure if you're standing here.
South American pressure. try this out, that you will be doing this in more complicated setups in the next weeks. So you should be able to do this right away very easily. If you're not, it's good that I know that. You copied it? No, don't look at that. Oh, TD, transitional dynamics equation. Who did it without cheating? Do it by yourself without looking at that. Did you find it out? Not yet? What are you finding hard? What are you finding hard? So apply the equation below, you know?
So
That implies that here,
t plus 1 equal to
yeah, just replace that. So replace little kt plus 1 by little k star, right? So now that is this little k star, there is little k star, there is little k star, and then you're going to have just one equation to solve for little k star based on the parameters. Did you? Okay, so it's just about replacing little kt plus 1 and little kt with that little k star, right? Who got it without cheating? Okay, you are very honest, and I'm very worried. Huh? The answer? I will work it out now. Okay, so we have two equations there. The first one, which is the TD, and then the other one that assumes the long-run equilibrium, right? What this is telling me is just simply replace whatever is kt plus 1 or whatever is kt by little k star, right? So it's just little k star equals little s a little k star alpha plus 1 minus delta little k star. So what I'm doing there is just using the second equation in the first equation, right? It's imposing the steady state equilibria already in our dynamic equation, right? Sometimes things are simpler than what they look like, right? So it's not that hard. We just replace, assume this long-run equilibrium is reached, and then we put that in the equation. So now, one more minute, and you find it out. Useful thing is to put together the linear terms with the nonlinear terms. What is nonlinear there is the term to the alpha. So we can put together the linear terms. So I'm going to have little k star, and I'm going to bring the 1 minus delta k star to the left. So that would be this. That is equal to little s a little k star to the alpha. I'm just working out this equation a little bit more and brought the term on the right-hand side, the linear one, to the left-hand side, right? So now what can I do there? If you realize here it's just that. Those terms cancel, and we got that equation there, which basically is almost done. We do have now little k star is equal to SA delta, and here that. So I'm just, things that are being multiplied in one side of the equation go divide into the other side of the equation. More formally, it's just you multiply by the inverse of whatever you want to cancel, and that goes to the other side of the equation with the inverse operation. So then this is little k star divided by little k star to the alpha, that is equal to little k star to the power of 1 minus alpha, right? Because the exponent of little k star is implicitly just 1. And when you have dividing these two things, you subtract the exponent. So it's 1 minus alpha. And that is equal to little s a delta. And then we can further, what else can we do there in order to find out just little k star? I can raise all to the power of that. What I'm going to do now, that means that I'm going to do some operation. I don't know if you do that, but I learned this from my teacher, and I copy that. So I'm going to raise everything to the power of 1 over 1 minus alpha. Right? By doing that, I actually get to cancel this term here, right? Because it's going to be, I'm going to keep doing that up here. It's little 1 over alpha, all that to the power of 1, and it's equal to little s a delta If I raise everything to the power of 1 over 1 minus alpha, then I'm done, because actually these two things are going to cancel out. So 1 over 1 minus alpha divided by 1 minus alpha in the exponent, and those cancel and they are equal to 1, and that implies that my equation is just little k star is equal to little s a delta to the power of 1 minus alpha. That is our final expression for the long-term value of capital per capita. Now, I want you to be very honest and raise your hand if you didn't follow all this. Okay. So we're going to do exactly the same thing in tutorials, although it's going to be slightly more complicated. There's going to be just one more term there. Okay? So you will have time to work this out. Here we're using basic mathematical operations that you need to review. Try to review this, what we use here. Equations. When things are multiplied on one side, they go dividing to the other. When you have an exponent and you get that exponent out of one side of the equation, then you raise everything to the power of the inverse of that exponent, and these exponents are going to cancel out. Okay? Remember, I got consultation hours, you have tutorials, so if you need to improve this, it's just a matter of working on this. Okay? So, this is the result. Right here. Right there. Exactly what we just derived. The level of capital per capita in the long run depends on saving rate, level of productivity, depreciation rate, and alpha, which is the importance of capital in production. And now, if we want to know the level of GDP per capita, which is what we care about, we know from before that GDP per capita, little y, is just this. We did that before when we divided the production function by n, little y, it's just equal to that, which means that little y star in the long run, GDP per capita of an economy is just this, And it's just the formula above, SA delta to the power of 1 minus alpha, all that to the power of alpha. Okay? Which is just alpha divided 1 minus alpha in the exponent. So that is the level of long-run GDP per capita. Okay? So this is why we talk about conditional convergence. What is this saying? This is saying that economies that share the same little s saving rates, essentially, economies that share the same A, like the level of technologies, or economies that share the same level of, the same alpha, which is the importance of capital in production, they will converge eventually to a same level of GDP per capita. Right? So this is what it's saying. This is not saying that poor countries will become rich eventually. No. This is saying that alike countries will converge to a similar level. And that is actually what we observe in the data. This graph here tells us this. This graph has, in the x-axis, the initial level of GDP per capita in 1950. And the y-axis has the ratio between GDP per capita in 2010 and the initial level of GDP per capita in 1950. And this is 1950. What is the meaning of that negative slope there? Who can tell me what is that meaning? Yes. Which means that countries are converging. The fact that this is negative slope, downward sloping, means that countries that started out, say, over here, at that level, 4,000, say, 4,000 US dollars. They started there at the initial of the sample. These countries out here, I mean, there is an outlier out there, but on average, these countries up here grew up much more than the others, because that ratio is larger than for other countries that were richer at the initial level. So this is saying that poorer countries grew more than richer countries, but this is not in the whole world. This is for the group of allied countries in the OECD. If you do the same graph for the whole world, there won't be potentially anything. It's just a mess. It's nothing there. But when you boil that down to the group of countries that are alike, like OECD countries, you will find that there is this kind of convergence. Yes? These are the OECD countries that were OECD countries long ago. So you don't have Chile there, Turkey, or Mexico, for example. These are the most alike type of country. But for the project part one, you will do this as well in a more sophisticated way. Because here it's not just about picking a sample of countries. You could also say, you know what? I will pick the set of countries that have similar saving rate, similar level of technology by some parameter that you might pick. And those countries should display this conditional convergence. And you can show me that. You can do it in different ways. Okay? Good. So I think it's time to stop unless you have questions. Pick the topic with your groups by next week. Otherwise, I will just assign you some institution. Sorry, pick the institution. Your group, pick whether you want to be economists in the IMF, in the World Bank, or the RBA, or whatever. Decide that. Email me. If you don't email me by next week this time, I will just assign you to some institution. Okay? Have a good weekend.